Weaver County deputies say drones are changing the way they
As a
handle
sheriff's officer, search and rescue drone flew high above this canyon, where they ultimately located two.
The drones are also used to help lost hikers, send messages, and transport small items.
The British Amazon has since announced it will start to use
Autonomous drone delivery could finally be coming to your front door.
One technology the government in this region has really taken to heart recently, and these things, the drones.
Drones is probably something that you've heard of before. Drones are self-flying autonomous vehicles capable of doing a variety of tasks such as search and rescue, remote sensing, agriculture, and whatnot. What makes drones so sought after is their agility, cost effectiveness, and their ability to carry good amount of payload. They can also be deployed into dangerous situations to reduce the risk of loss of human lives. Avoiding obstacles helps to keep the surroundings safe. Fatal injuries can happen, let's say if a drone crashes into a human being. To tackle this issue, my project aims to use reinforcement learning techniques for the task of obstacle avoidance for quadrotors in simulation and then to deploy it to a real hardware for a sim-to-real transfer. Moreover, I use Agilicious, a hardware software framework capable of doing highly agile flights. It is a state-of-the-art platform in terms of agility and onboard compute capability. This Agilicious platform has possibly been tested for the first time in the United Kingdom. I'm Reba Vojha, and this is my screencast for my third year project. Join me as we go through some background information, product demonstration, and evaluation for the product developed in this project. Traditionally, the task of obstacle avoidance can be broken down into perception or localization, planning, and control. Imagine you have all your fancy AI algorithms ready to be deployed on the drone. You set up everything, but as soon as you launch it, oops, it crashes. This is because it is necessary for the flight controller to know about its whereabouts to control the drone appropriately. In this project, a motion capture system has been used by putting cameras around the drone's arena within a 3D space. After getting the vehicle pose data, the flight controller would be able to control the drone successfully. Second comes the planning, which generates safe and obstacle-free waypoints for the drone to follow. Third is the control. It helps in closely and accurately following the trajectory points generated by the planning block. Here we can see the points have been connected with a blue line. However, the drone won't be able to follow such sharp trajectories due to it being an underactuated system with 6 degrees of freedom but only 4 control inputs. So beta-spline trajectories can be used which are smooth and easier to follow for the quadrotor. Here is an overview of the localization, planning, and control pipeline. Having a separate planning and control block creates a gap between the two during deployment stages. Instead, we can use a neural network which directly maps data from the localization block to the drone without the need of an external planner or a controller. This neural network can be trained using reinforcement learning. Reinforcement learning teaches an agent to learn through trial and error in an interactive environment using feedback from its actions and experiences. Let's understand this with an example. To teach a dog to sit, we reward the action of sitting and withhold treats when the dog stands after the command. Through this, the dog learns that sitting earns rewards, encouraging it to repeat the actions for the treats. Here are some of the key terms used in reinforcement learning. An agent is an entity capable of perceiving and interacting with its environment. A reward is a numerical signal indicating the desirability of an action. State is the current situation of the environment as perceived by the agent. Action is a decision or a choice made by the agent that affects its environments. Various algorithms exist in the literature. In this project, proximal policy optimization or PPO was used. As quoted by the researchers in OpenAI, PPO has become the default reinforcement learning algorithm at OpenAI because of its ease of use and good performance. PPO works by collecting data by running the policy in the environment and updating the policy using this objective function. This function denotes the empirical expectations over a batch of experiences at a given time step. RT theta here is the ratio of probabilities of taking action AT under the current policy to the probability under the old action at state ST. A hat here represents the advantage estimate at a particular time t, telling us how good it is to take a particular action. The cliff function essentially prevents extreme updates, ensuring stability during optimization. Overall, this equation helps us balance between exploring new actions and exploiting known good actions, which is important for training stable and effective reinforcement learning agents. Now we'll look at evaluation of our reinforcement learning agent. This plot illustrates the mean episode length and reward during training. Initially, the drone crashes early, yielding lower rewards. Over time, the agent learns to maximize flight duration and rewards. This plot depicts the distance from the target over time. At time step 0, with no training, the agent crashes quickly, while at 2 million time steps, it performs the best, nearing that target point closely. Now let's see how the agent performs in simulation. Here we can see the performance of agent at various time steps during training. Initially, the drone frequently goes out of bounds, crashes into obstacles, and has minimal flight time. With continued training, it learns to find the quickest way possible to the target efficiently, avoiding obstacles and maximizing flight duration. Here is a pi flight simulation with obstacles in between. Next, we will look at the hardware implementation part of the project, the sim to real transfer. This is the first flight of the racing drone using Agilicious in a lab. Quite an interesting reaction by the audience. 3, 2, 1. Here we test the maneuverability of the drone by commanding it to go to various positions and then to land. This video shows the reinforcement learning obstacle avoidance algorithm deployed on the real hardware. Here are the results achieved in this project. I assembled the Agilicious racing drone completely from scratch, soldering each of the necessary parts such as the flight controller and the electronic speed controller, flashing the NVIDIA Jetson Heavy NX onboard compute unit, and manual wiring. I also created an RL agent for the task of obstacle avoidance for quad rotors, which produces control commands directly from state inputs. Finally, the trained RL agent was deployed on the hardware for a sim to real transfer. So this was my screencast for my third year project. I hope you enjoyed it. Thank you for watching.